Long day. So I'm going to describe to you today two big instances of phenomenology that can be derived from these predictions from inflation. One is the CMB. I'll go through some of the details of what has been observed in the CMB today. And then the second one is logical action, which is now in full thrust. Okay, now we have many different experiments searching for the distribution of matter in the universe. Okay, let me recapitulate a little bit of what we were saying on Tuesday. If you remember, we were describing temperature and substrates arising from gravity, mostly, you know, the usual redshift dependence of temperature fluctuations or frequency fluctuations of a fluid with respect to the metric, Newtonian potential, stereometric fluctuation. This is also not just the perturbations on the last Kaplan surface, which indeed determines blue shift or redshift of photons which travel towards us, but also if the potential varies in time since the time of last Kaplan until today, it will also induce an effect. It's called the integrated Saskowitz effect, and it will be crucial in models in which the universe is not matter-dominated. For instance, the universe where in the last few stages of evolution of the universe, it started accelerating, like we know today, because of the lambda matter contribution. Okay, so this term, ISW term, will be relevant, and in fact, it might be one of those terms that will be responsible for peculiarities or anomalies that we observe in the CMB, like the gold spot. Okay. Then there was the density contribution, remember? The fact that you have the photons coupled to the baryons, and those baryons living in the potential wells of dark matter means that if they are strongly interacting through electromagnetic interaction, Thomson cross-sections, it's a very tightly coupled fluid, so variations in the baryons are going to affect variations in the photons. Vice versa. If they're adiabatic, then there is a direct relationship between the fluctuation in the photon density and the fluctuation in the baryon density, or the matter density. So rather than having a factor 1/4 delta rho in photons, we have 1/3 delta rho in baryons. Okay? With respect to temperature. And finally, we have the usual Doppler effect. Okay, so these three effects are relevant on different scales. You will always have gravity effects along scales, but they're certainly dominant on the very large scales before the density and the velocity contributions are relevant. On very small scales, baryons go through acoustic oscillations, and they are inducing these fluctuations that I was describing on Tuesday. But on large scales, these are the dominant ones. These are called the Saskowitz effect, and we were describing this the other day. Let me go through some of the equations. For adiabatic perturbations, there is a relation between the density fluctuation and phi. We substitute here, phi minus 2/3 gives you 1/3. So we know what is the relation between the temperature fluctuation and the metric fluctuation, which, remember, was related to the curvature fluctuation produced during inflation. That's how we made this connection. Geodetic from the early universe to the late universe, plus the integrated Saskowitz contribution. So there are two terms. During most of the evolution, since the last Kaplan surface until today, phi is constant. It's dominated by matter. Photons do not get affected in their frequency from the fact that they're traversing through the period where the phi is essentially constant until the universe starts to get accelerated because of the presence of this cosmological constant. So in the absence of curvature, in the absence of cosmological constant, phi is constant in matter-dominated universe. When you include it, then it's no longer constant, it starts decreasing. Okay? And this decrement is going to give you this potential. So the way you do it is, you take these to be the eigenfunction of the Laplacian. So you have a time-dependent term. This is the thing that we evaluate in terms of curvature, and we can compute from this equation its explicit time dependence during matter and lambda domination. And you have the usual eigenfunction of the Laplacian, which just satisfies this equation. It is well known in flat space-time that these eigenfunctions can be split into Bessel functions, spherical Bessel functions, and we will use this to compute the CLs.
Sorry.
Yes.
Yes? I think a pertinent question for many was Of course, in the last equation, Laplace is assumed, or GR+1. What are the previous equations? Is there any assumption about GR, or can we rely on those expressions?
For instance, this is 2 times phi, it comes from phi plus psi. Okay? If there is somehow some slip, so that phi and psi are not proportional to each other, then it's rather than 2, you'd have something else. Okay? Moreover, at last happening surface, if you have variation, for example, so you have a different scalar tensor theory rather than a gravitational tensor, then you have a different dependence on phi. Remember, if you violate the weak equivalence principle or the strong equivalence principle through some equation W, it will appear here. Okay? It's no longer true that the frequency dependence of the photons will be related to phi exclusively. There might be an effect due to this extra couplings. So I am assuming GR. Yes. The explicit expressions, let's see, yeah, I think they have been worked out, of course, we try to give you the references.
It's also worth mentioning, historically, of course, the leading term, the Sachs-Wolf term, is the way it is because Kohlberg matter really dominates.
That's right.
If you go back to, to the time when we thought the universe was open, there'll be a pressure suppression term.
Definitely.
So
if there is curvature,
there's going to be something.
Absolutely. Moreover, if there is curvature, you no longer have your eigenfunctions of the Laplacian being written in such a simple term. And we worked this out with David Live and others in 1995, as you know. So indeed, there would be not just a continuum of modes, which is what you have from k equals 0 to infinity. In the case of an open universe, since you have curvature, there will be a discrete mode, this famous supercurvature modes. And then you will have the continuum afterwards. So from k squared equals 1. So it becomes much more involved if the universe is not flat. Fortunately, today we simplified our lives because the universe seems to be extremely close to flat, to think 1 per million. Okay? But certainly, in the 90s, we were envisioning the possibility of not having a flat universe, and these have been changed. Okay. Right, so what do? We look at the CMB. Suppose that you're at the center, okay, and you're looking at the CMB. Your CMB is, I'm projecting a sphere into just the circumference of a circle, and I'm looking in different directions. What I'm asking, for a given angular separation, what is the correlation between the temperature in that direction and this other direction? Of course, these two vectors, which are spanned by an angle theta, can be pointed out there, at multiple places, right? Depending on the angle. If you have just 180 degrees, maybe you have a few ways to point this angle all over the sky in an independent way. So we will see that this will be crucial for the cosmic variance arguments that I will go through. Okay? So if you do this two-point correlation, I think I have the equations just further above. No, or maybe they're below. Just a moment. Check. Yes, here they are. So I can ask, what is the two-point correlation function in temperature fluctuations spanned by an angle theta? We can expand this in legendary polynomials for the harmonics, combination of those, and these coefficients, CLs, the power spectrum, can be computed for what we predict for inflation, an amplitude and the power law with just a fixed index. Okay? In the particular case in which you have a scaling variance, n equals 1, then this is extremely simple. You just multiply those coefficients CL by LL plus 1 and you get a constant. That constant is going to depend on the physics of inflation, the rate of expansion, and the slope of curve. So let me go back then. If we then plot, sorry for the, it's not very bright here. If you plot CLL plus 1, here you would get the Sachs-Wolf plateau. If you would have had no lambda contribution, this tiny increase towards smaller L's corresponds to modes that are now entering the horizon. If the universe is very fast expanding, let me draw this here, those modes, some of these, will not enter the horizon. This is the horizon during inflation and during matter and radiation. remember that matter radiation equality and photon decoupling occur very close to each other, and this will be seen today. Okay? So, if today, indeed as we have noticed, is dominated by a cosmological constant, the rate of expansion is such that the horizon becomes constant. H inverse goes to the constant. It's not growing like t, 2 or 3 times t, but actually becomes constant. That means that those modes which were growing exponentially during inflation went out of the horizon during inflation, remained constant outside, and then re-enter. Some re-enter and go out again. Some don't even enter. Okay? So there will be modes which had been outside the horizon, and if you would have continued to be matter dominated, they would have re-entered the horizon. Just simply, our horizon would become larger and larger and larger, and encompassing more and more modes. Eventually, those modes don't enter. The contribution of that effect to the two-point correlation function is this rise of the two-point correlation function homogeneous. Okay, so these produces both plateau, the first compression peak, those scales that enter the horizon right at the time of the coupling, those modes. Okay. These are the ones that first enter into compression, they produce the, well, first enter exactly at the time of the last scattering, precisely when one made the photograph. Those, or snapshot, those other modes which enter earlier, which went through rarefaction, compression, and compression, as I was describing on Tuesday, they will be also diluted because of the width of the last scattering surface, which introduces diffusion, and this decreases the amplitude of the fluctuation. And this is the reason why you will see in all images a very rapid decrease of the amplitude. It's called silt damping. Okay, for the scalar contribution is this, for the tensor contribution is this other line. Okay, so you have both scalar and tensor contribution to the temperature and exhaustion. And this can be seen here. The scalar has the shape of advertising. Depending on the ratio of tensor to scalar amplitudes, you would have this for half this behavior. So when the fluctuations, gravitational or tensorial fluctuations, which act like any relativistic species, enter the horizon very quickly, decay over and forth, the amplitude decreases. Therefore, there will be both gradient and curve components of the polarization. I'll describe it slightly more later on. And depending on this ratio, you might have something which is visible or possibly undetectable. We'll see whether we can get it. Now, notice that this seems quite straightforward. You just have to know what is the amplitude and determine the parameters. Unfortunately, those different parameters, cosmological parameters, they're not set up by inflation, they're set up by the reheating of the universe. It depends on what different components of matter and radiation existed or were created at the end of inflation, and therefore still we do not have a theory that can predict explicitly what is the relation between the amount of matter or the amount of cosmological constant or the rate of expansion or the baryon content. All of those different coefficients or parameters in cosmology have to be determined by observations. Okay? For the moment, we do not have a fundamental theory that will connect those. Perhaps eventually we might find such a thing. So in the 90s, the possibilities were extremely varied. You could have these are the two-point correlation functions, so the angular power spectrum is a function of multiple for different models. You see here the variety. Okay? So one had to measure those things. It's clear that there are degeneracies in the determination, so we will have to do a multi-parameter fit, and that's indeed what the experiments WMAP and Planck did. WMAP, the Wilkinson Microphotometry probe in 2003, measured not just what COBE did, which is the extreme homogeneity extreme isotropy of the universe in all directions. This is due to our motion with respect to the CME. We're being attracted to the great attractor, and this induces a dipole. You can see a little bit of the galaxy, which is very obvious when you subtract these two modes, the monopole and the dipole. These are the quadrupole and higher multiples of the CME. It's clear that this quantity, which is the galaxy, is going to be a nuisance. Moreover, it looks a nuisance for temperature, for polarization was crucial. That's how it was described. Well, the history of the CMB is a history of improvements in the determination of those anisotropies. You go from 1965 to 1992, 2003, 2013. Higher and higher resolution. In 2002, we already had a very clear indication from multiple number of experiments of the CMB, not just satellites, but also ground-based experiments all over the world, which showed a very clear peak, and then somehow some acoustic oscillations. It was not clear. However, in 2013, with the first data from W, well, before that, but these are the data from that before time. We had from the Atacama Cosmology Telescope and the South Pole Telescope, it's a very clear indication that there were more than 2 or 3 peaks in the CMB. Finally, with Planck, power spectrum 2015, we settled the issue. The universe behaved exactly as predicted by inflation, 30%. So this is the type of curve where you can obtain with just 6 parameters. It's extraordinary. You can give account for essentially 2,500 data points with 6 parameters. That's rarely in something easy to obtain. Okay, in cosmology, this is quite extraordinary. And the reason is that there is a paradigm, that is inflation, which sets up the stage for the rest of matter to behave according to its principles. Okay. If it weren't for inflation, we would not be there. We would not be able to get such curve. Okay. Now, what are we really looking at? We're looking at multiples, especially with all those high resolution ones, the high L. And different multiples in space correspond to different configurations of fluctuations. So you go from L plus 2, 3, 4, 5, etc. And you ask what is the amplitude at each one of these L's. But remember that depending on L, especially at low ones, you don't have that many realizations. So this is L equals 0, the homogeneous universe. For L equals 1, the dipole, in principle you have 2L plus 1 independent realizations. Here you have 3 for L equals 1. For the quadruple, 5. There aren't so many ways to fit, if you want, a quadruple in the sky. Just 5 independent ones. So if it happens that one of those is just behind the galaxy, you're done, because you've lost 1 of 5. Okay? And you want to get from here a Gaussian distribution, take the mean, and determine from there the amplitude. So the fact that you don't have that many realizations within your own universe to measure a quantity is called sample variance. In the case of the universe, that corresponds to cosmic variance. Okay? So cosmic variance is going to be a nuisance for us. Of course, the higher the multiples, the more realizations we have, and therefore the better sample your Gaussian might be. And then you can get the mean much better. Okay? Well, higher until you get to the same mean. You have thousands of multiples for high values. Okay? So, actually, these little dots that you see here, the gray dots, correspond to all those different realizations that WMAP was able to measure. Normally, you don't see such a figure, because the only thing you're given is those data points with error bars and a curve that seems to fit extremely well. Okay? But they're made out of many, many different realizations. Okay? Fortunately, if you have many of these, you can get a very nice value with a small error. Okay? But, in fact, you do have plenty. 2L plus 1 realization for Gaussian. You sum over all of those, assuming that these are Gaussianly distributed according to inflation, and you get your CL. And then you compare with that. Okay? So it's crucial that you realize that not only for small angles you're bounded by your resolution of your experiment, but you're also bounded on large angles by these cosmic variance. There are certain aspects like this that you cannot, or even very low particle, that you cannot account for by ordinary physics. Perhaps there is physics there, yes, but we are always subject to the constraint that we happen to live in a particular part of the universe. If we could go to the other side of the universe and see another 5 radio stations, we would be able to lower this cosmic variance. But unfortunately, we can't do that, right? We're stuck to our Earth or our surroundings. So the thing to go is to high resolution, Bellido and Planck. This is Planck 2015. This is the correlation function. The higher L's. It's extraordinary, really. And from here, one can determine whether the universe is open, flat, or closed, as we were discussing a minute ago, because different geometries, spatial geometries. Sorry about this. This is a 2-dimensional projection of a 3-dimensional space-time, space. Flat actually should be drawn like a cube. Okay? So I'm looking at the 2 projected 3-dimensional space here. Now, the projection on the sky is such that if you have, this is the size of your horizon at the scattering surface. So if the universe is perfectly flat, that is Euclidean, the trajectories of photons would go along straight lines. That's what light does in a Euclidean space. Okay? And therefore, the angle subtended by the last scattering surface, it's given by what you predict from the time at which the photons left, because that gives you a scale. That scale can be compared with the angle that you observe, and from here determine what is the curvature space. If it happens that the universe, rather than being flat, would be open, then it would have photons would not travel straight lines, they would converge inward, and when it reached us, we would have the scale corresponding to this last scattering surface projected on much more angle, much higher L. Okay? Therefore, one can determine from the position of the peak, from this one, where this peak is going to tell you, and not just this, but all the subsequent ones, it's going to tell you what is the curvature of the universe. In pictorial way, this is what WMAP observed, and high resolution what Planck observed. This is what it would have observed if the universe was closed, and this if the universe was open. The fact that it did observe this with the same scale to 1 part in 10 to the 3 is the best evidence we have that the universe is flat. No other measurement is as precise as this one to tell you the universe is flat. Okay. Of course, there would be a limit if we increase the sensitivity and we go to a scales which are of order, say, 1 part in 10 to the 4 in curvature. Then there's a moment which we cannot distinguish between the background and the fluctuations. Because what are fluctuations? They're nothing but curvature fluctuations. That means that in a certain direction in space or another, those fluctuations are going to change the curvature of the universe. Therefore, we cannot tell whether the global curvature of the universe is 10 to the minus 4 or it actually was induced by the fluctuation on the CMP. Okay? That's crucial. There is a limit to the way we can resolve the flatness of the universe. We cannot go below 10 to the minus 4. Okay? Let's go on. So for the moment, the only thing we know is that somehow some mechanism must have made this thing extremely flat. Not only do we have curvature, we also have the effect of the matter distribution between the CMB and us, which acts as a lensing field for those photons to travel across. If the matter which is distorting space changes the direction of the photons, remember, maybe I should emphasize here, it's not that the universe is perfectly flat or Euclidean. What has happened is that those photons are actually moving along trajectories which are deviate from each other because of the presence of matter, but sufficiently little that the trajectories essentially align. And this angle corresponds to what you would expect from a global curvature being flat. However, there is matter between us and the last scattering surface. This matter, just as the sun between the star and us creates a deflection of light and induces a change of path, it's going to change the path of photons from the CMB. That's called lensing, CMB lensing. And the CMB lensing, which was a prediction from long ago, actually it's extremely useful to constrain models of modified gravity, because the way the trajectory of the photon goes from the CMB to us is extremely dependent upon the nature of gravity. How did gravity act from a given mass distribution on the photons will depend on the theory of gravity. And here you might look for deviations with respect to general relativity. Moreover, since those deviations may happen along the way, it could be that modifications of gravity close to us will affect the lensing of light in a way which is different from modifications of gravity early on. Okay, so we might tell when did that deviation occur. Okay, so this is what the CMB lensing has been measured by Planck. You see here, this is the galaxy. This is on the very large scales, what you would expect from the mass distribution. And the cross correlation between the field corresponding to lensing, what's called the curvature, or sorry, not curvature, the convergence field, is actually extremely good. The predictions of this curve, and this is the data point from Planck 13 and 15. So it's a detection to the level, I think it's 50 sigma or so. So now we know that indeed CMB lensing has been observed. Well, I'm not going to bother you with the amount of data that Planck and WMAP has produced. I will concentrate perhaps on these parameters. So you can determine to fantastic precision some of the parameters, the amount of barriers. NS to few percent. Here even to few per mil, if you include magnetic oscillations, I'll describe now. So some measurements are exquisite with Planck. The fact that we have 2,500 multiples, independent measurements of the cross correlation, it's extremely powerful to produce below percent determination of most of the cross correlation parameters. These are the fundamental 6 parameters that I was describing a while ago, I was mentioning. And these are deduced parameters, those that you can infer from these 6. Right, so not only do we have energy, temperature for those photons, we also have the polarization of those photons. And the polarization actually has its own anisotropies. We can break this polarization field into the gradient curl component that we call E for a generalization of the electromagnetic field, not because this has anything to do with electric or magnetic field, it's just the gradient curl component of the polarization. And it's very similar, the effect that we do in order to measure, you just put a polarimeter and you determine whether light is linearly polarized in this direction or this direction by seeing the amount of photons that go across the polarimeter. Not all frequencies in not only WMAP, also Planck, had a polarimeter, unfortunately. Only the high frequency instruments, and only 3 of those 5 in the high frequency instrument had a polarimeter. And that was quite unfortunate, because we would have loved to have polarimeters on all the high frequency and some of the low frequency instruments also, but there wasn't any. How does it work? Well, the last scattering surface, it's the place at which photons last scatter off electrons. So what do they do when you have a photon that comes on an electron? It just makes it oscillate this way and then re-emits in the orthogonal direction. So you have a photon that comes here, interacts with the electron, and then re-emits. If you have different number of photons coming from this direction to this direction at 90 degrees, then if they're the same, then the linear polarization this way and the linear polarization this way cancel out. There is no polarization. So if you have a quadrupole, if you have slightly more photons coming from this direction than from this direction because of the anisotropies in the distribution of matter in the last scattering surface, then you will have a small linear polarization. Not everything will be cancelled out. This small linear polarization of the order of 10% is what is going to make the amplitude of the gradient and the curve polarization so much more than the amplitude of the temperature polarization. Sorry, the temperature on its own. Okay? That's in general the reason why you observe, so it's so difficult to measure the polarization of the CMB, not only the gradient, but also the test. Okay? So the Thomson scattering is proportional to the product of the incident and outgoing wave, and proportional to the scattering cross section. And there are, as I said, E and B modes, which correspond to curve and gradient modes. So you have the gradient mode, it's rotationless, we call it E polarization, and it has this shape. It has two types, this and this, and they are related to hot or cold spots. If you have a cold spot, then your plane of polarization in the linear and the gradient mode is radial. If it's a hot spot, it will be tangential. Okay? Now, in the case of the B polarization, which is divergenceless, it will have a handedness, like any curve. Okay? So, around hot spots, its handedness is this. Around cold spots, it's the opposite. So, you can immediately determine, by looking at the sky, where are the hot and cold spots, and ask, what is the curve around these?
So what's the reason for the hot and cold spot correlation?
Right, if you have a gradient, okay, imagine that the temperature is not uniform, okay? Yeah. You have a hot spot, and you have a gradient. The gradient is going to give you a direction, okay? Yeah. Now, the gradient is also inducing a direction on the photon, on the scattering of the photons when it reaches you. Right. So it's going to give you a linear polarization along this direction. Right. In the case of the B component, since it's a tensor contribution, it's no longer a gradient, okay? It has curl, and it comes from the part of the polarization which is not a gradient, okay? It's curl. Then it's rotating, it's twisting, if you want. It produces shear. It twists the plane of polarization with respect to what you would observe. In fact, thanks for asking, because that's crucial. If we have, this is assuming that nothing happened between that scattering surface and us. But if by some reason something intervened between you and the last scattering surface, which induces shear, matter we know, induces shear, then the plane of polarization is not going to go straight to you, it's going to be twisted. And it might induce on its way, through lensing, a change from the E mode polarization into the B mode polarization. That is called B mode polarization induced by lensing. Okay? And this is going to be a nuisance, in fact, because we will have to know to great accuracy what is the mass distribution between the last scattering surface and us in order to subtract the contribution to the B mode lensing from the matter contribution in between us and the last scattering surface. Okay, so this is the temperature linear polarization gradient term as for multiple numbers bigger than 30, and you see here, these are the data points, and the curve is what you would have inferred from the temperature fluctuations. So there is no fitting here to parameters. We're not fitting these data points with a curve. No, the curve is what you would deduce just from the temperature fluctuations. This is showing that the whole picture is very consistent. Okay? We're not doing a fit with this figure. Actually, you see that there are slight deviations from what you would expect, which has some component, but it's certainly well below the systematic fluctuations of these data points. Okay? The same happens with the EE, the self-autocorrelation of the gradient polarization of the photons from the same. So this curve in red is what you would expect from the temperature, and these are the data. So it's fantastic. How well do we know the CMB today, at least from Planck? Now, of course, the holy grail, the thing that initiated the whole business was trying to understand whether inflation had something to do with the anisotropes we observed in the CMB. So we would like to know what is the scale of inflation. We would like to know whether there's a smoking gun of inflation, which could tell us not just that indeed something like inflation occurred in the early universe. It seems it was extraordinary, the prediction that it made, and it seems to, at least it's perfectly consistent with what we observed in the CMB, but we still do not know whether inflation was the only possibility. So if we would have measured, and eventually I hope we will, the current component of the polarization, which is only possible to be generated because of the tensor contribution of the fluctuations we were discussing on Tuesday, then we might be able to determine not just that inflation was responsible for those, but also what the scale of inflation is. So there has been this tremendous run for it. Many different experiments have tried to find this B-mode polarization, famous B-mode polarization. And there are some experiments like BICEP who are a bit too hasty in advertising their results. There are others like Southpole Telescope, Atacama Telescope, and so on, which we're still taking data. In the case of BICEP, it looked at a region where the temperature fluctuations were particularly clean. So in this region, one expected that far away from the galaxy, it expected that it would have no contribution, not significant contribution from, now we all know, the horror word dust, the dust in the galaxy. Okay? We've already been through it. But at the time, it was perfectly reasonable to assume that the temperature and the polarization would be proportional to each other. The places where you have more contribution from dust in temperature should also be the places where you have small contribution in the polarization. Now, that correlation was broken when Planck came and showed that the region that BICEP had looked at was not devoid of polarization from dust. Okay. But BICEP, unfortunately, which only looked in a given frequency, 150 GHz, and did not have other bands like 100 or 300, could not get rid of the dust. And it produced this. So this is the total polarization at 1.7 microkelvin scale. This is 7. And you see there are very clear patterns, mostly dominated, as you see, by the E modes. Okay? This is the radial, tangential. So if we take out the E mode and take away this gradient and tangent component and multiply this, you see 1.7, you almost see no B mode signal. Then you go and increase it, have a high resolution, 0.3, then you start seeing the curve component. Okay? So, nicer picture is this one. We see the hot and cold spots. Now, it's quite interesting, and it puzzled many of us, and still is unresolved, is that if indeed these are primordial curl components of the polarization, then there should be at least the same number, since inflation does not break chirality, the same number of hot and cold spots. So you should have the same number of curls in one direction than in the opposite direction. Now, if you count them, and I have done it, there are 20 of each. Plus minus 1, it's perfectly chiral free. However, you don't expect that from dust. Dust, if it's distributed in a sufficiently large scales, will be concentrated in certain regions more than in others. So the effect of dust on the polarization of the CMB should be irregular, should be inhomogeneous. Why should there be more of one type or the other of chiralities? If there is dust, you should not expect to see exactly the same. Okay? It's only inflation which predicts equal numbers. Yes?
To what extent? So what would be the modification? What would the expected?
For instance, if you had more dust in this region, you would get to have more regions in one direction than in others. Because the way it creates this is because dust is aligned with magnetic fields. Magnetic fields are very homogeneous on those scales. Magnetic fields in the galaxy create both toroidal and spinodal curves, and these will induce on the dust a change in the polarization. So you would expect to see from the CMB, from the dust in the galaxy, that the CMB photons would have scattered off this dust and would produce a curve which is not equally contributing to one chirality than the other. And, surprisingly, the equal numbers. Of course, the area is not sufficiently large to make a thorough statistical
Yeah, so that was my question. So what would be
contribution.
the expected level of discrepancy between hot and cold? If you superimpose a perfectly chiral CMB...
If it's perfectly chiral, there should be no discrepancy.
No,
So if you have 20, 1 at most, you should have. In the case of dust, that depends very much on the dust distribution. You could have 2 or 3, or even 5. A large fraction of those would be of 1 chirality. Yes?
Are we talking about intergalactic dust?
Our dust.
Dust
No,
in
the dust in the
galaxy.
intergalactic medium doesn't contribute much. No. It's mostly the dust in our galaxy. Okay, so unfortunately, we cannot go above the galaxy. And these were the measurements of the Bicep and Keck 2014 component, which seemed to suggest that there was some kind of contribution to the tensor to scalar ratio. Then came along Planck, mostly with 353 gigahertz measurements, which contained the polarimeter. And if we would have been able to move up the galaxy and leave the galaxy behind, then we would be able to see the pristine CMB primordial polarization. Unfortunately, we are within our solar system, and we have to deal with dust. And the way to deal with dust is to model it. For this, you need several different frequencies, and using the extrapolation of the 353 gigahertz, Planck, the speed, Bicep, and Keck together produce a correlation, so multiple in the PB component, which was perfectly in agreement with what you would expect from lensing. Okay? So the signal, which was this, went away. So if you want, Planck plus Bicep have this contribution. When you added up 353, it just reduced the tensor to scalar ratio. But it did not show there was any evidence for R different from 0 at any sigma. In particular, if you take R and the amplitude from dust, so this would be all dust, no gravitational waves, this all gravitational waves, no dust, these are the controls. When you add up Planck. Or in the likelihood, expected peak normalized, in terms of R, it's true that there's a peak at 0.05, but within 2 sigma, it's 0. Okay? So the question is, do we have hidden between the inside here an actual peak, which is for the moment is dominated by dust, and the next generation of satellites will be able to pinpoint? Perhaps. It's not impossible. It is possible that there is such a component. But we don't know for the moment which one is it. Fortunately, there are other experiments online. There's Polar Bear, PCT Pole, there's the South Pole Telescope, there are some balloons like EVEX. And they will have resolution which is enough to tell R of 0.2 from, say, the total 1 order of magnitude smaller. This one from this one. Bear, EVEX is a balloon. Go down to a few percent. And in the future, which is not so far now, LIGO. This is a satellite which will be sent by the Japanese. It's an American-Japanese collaboration. And if these are the data from Bicep, these will be the data from LIGO. It's a full sky satellite. It's prepared to be launched. Okay, so we will have to wait for a few years. We don't have to wait for a decade. Perhaps in a decade we might have Core or Core Plus, a member of such a collaboration for CMB. It's an N5 mission from ESA. If it gets approved, in 10 years' time we'll have the required polarimeters in the high frequency instrument to be sent to the sky and measure the CMB polarization to exquisite precision, much better than that. But for the moment, it's just a proposal. It still have not been confirmed that it's acceptable. LIGO, in the meantime, might be able to tell us if the tensor to scalar ratio is bigger than 5 to the minus 3. For instance, if it's 0.01, it will measure very accurately. Okay? So, if it does measure at the level of 10 to minus 2 or so, then what does this tell us about the scale of inflation? This is the inflationary model suit that I was describing on Tuesday. Okay, here are a plethora of models of inflation. They're very different in terms of the scale of inflation. So you go from the hyperbolic tangent models, the alpha tractor, which is alpha 0.1, which has very small in log 10 contributions, so 10 to the minus 4 or so, minus 3. The Stavisky model, the Higgs model with different size, all the way down. There's a continuum of nodes for lambda 5/4. Or you could have, well, there's a whole variety. Some that are very specific, like M squared phi squared, which don't seem to do that well with observations. And the key point is that once we measure R by Lightberg or Core or whichever other experiment, and now there are experiments on the ground, not just satellites, like the Simons consortium, which are going to measure from the ground sufficiently large scales that they hope to be able to completely reach the level of a few percent in R. Now, if we measure this to some accuracy, it is going to tell us about the scale of inflation. And notice that 0.1, it's about the scale of grand unified theories. So if we lower here, say 1 order of magnitude, 0.01, then we might say that the scale of inflation, since this goes like factor 4 of the scale, 2 to the 4, 16, then we're only going to lower a factor 2 in the scale of inflation. So in order to really go down with respect to the grand unified theories scales, we will have to be able to measure R to exquisite precision, to 1 part in 10 to the 5, 10 to the 8. And we're very far from that. That's science fiction. There is no method nowadays designed to be able to get rid of both the lensing and the dust to go down to such a small number. So we're stuck with this. We'll only put upper bounds on the scale of inflation. Maybe we're lucky and are sufficiently big that we not only make an upper bound, we also do the measure. Yes?
So what's meant exactly for the scale of inflation? Is it
okay.
The field value?
It's the fourth root of the energy density during inflation, 65 field volts before its end.
Okay.
So draw it here. So imagine you have, remember the variety of models we have. No? This, right? All of these have a scale above 0. It's this scale. If you write it as that gives you scale. And that scale is 10 to the 16.
And it's not necessarily trivial how this relates to the reheating temperature, for instance. But we don't
Not at all. The reheating temperature will depend very much on the microphysics. We'll discuss this tomorrow.
Okay.
Very much. And we don't know that microphysics. Okay, not only do we have R, which is obviously one of the aims of most of these experiments, we also can measure the running of the tilt, the variation of the tilt, the scale. And surprisingly, compared to this one, where you have tremendous range of orders of magnitude, from 0 to -4, in the variation of the tilt with respect to scale, we don't have such a great change in ranges. In the whole with R around 10 to -3. That's quite surprising. That's something we realized with the other Röst a couple of years ago. Somehow, the whole variety of models that we were finding in the literature, they all seem to cluster in the variation of NS with respect to scale. So this would be a very nice way to test the theory. If we find that the variation of NS is much faster than you would expect, then all these models will be completely ruled out. So rather than using R to test inflation, we might use this to test inflation.
Isn't it hard-coded into the inflationary paradigm that doesn't allow you to get a value?
No, because the only thing we measure, and that will be crucial for tomorrow when we talk about primordial black holes, because the only thing you measure are 10 E-folds. Something could happen beyond those 10 E-folds. You have this potential. These are the scales in phi that correspond to the CME. So this could give you a very flat spectrum in the CME. So this, if if we draw it here, let's see, it would be your power spectrum, which does this. This is P of k, very large scales, small k, and your tilt is ns, smaller than 1. 1 would be this, okay? And it's running. It's running, it's going to give you the curvature. Now, the range of k's that you probe is so small that you don't know what happens here. For instance, you could have a peak, you could have a plateau, and this plateau will produce a peak. Okay? So knowing what happens 60 EFOs before the end of inflation tells you nothing really about the whole dynamics of inflation. Okay? As long as the number of EFOs from here to the end, 565 to the end of inflation, is 65, which gives you our scale today, depending on the reheating temperature, of course. That's all you know.
So it's unlikely to
It
make
could
a model.
perfectly change.
So it's really unlikely to make a model where you'll be far outside that.
It's perfectly viable. Where the variation of NS is much faster than what you get from here. It is possible. For instance, these models. I was discussing with such a plateau. You will do this. So you will already see very fast change.
So
Yes.
for each of these models, you're drawing a little line.
Yeah.
What parameters vary?
Okay, the number of EFOs.
Yeah. Okay.
From 50 to 60.
Okay.
Here I was very, thanks for pointing, I should have said. Okay? From 50 to 60. Some models, the range is larger. But still, 50 to 60 is described here as a variation because we don't know the way the reheating of the universe occurred. If it's very fast, then it's not 50 but 60. And if it's very slow, then it will be 50. Okay? It depends very much on the reheating temperature compared to the scale of inflation. Yes?
How would the mean point in that diagram change if I change, say that I require 80 to 100 EFOs instead of 50 to 60?
You would go all the way out
Okay.
of the Planckian.
No, but because I'm asking, so what's so special about -3 or one
I don't know.
over 1,000? And I wonder if we...
For those models, the link between the number of defaults, the tilt, and the amplitude already imposes such a constraint. It's surprising. I don't know. It has to do with our model building. We probably are not ingenious enough. And as I'll show you, indeed, on Friday, tomorrow, there are models where the variation could be much faster and would have new physics. So it's just simply that we had not thought of those before.
It is only for models based on the potential?
Yes, that's right. You could have changes in some of these. For instance, the Higgs inflation, you have non-minimal coupling. But you always can write. You have them in the notes. I don't know whether you want me to go through these. It's there in the notes. I thought it was enough to find them there. But if you want me to go in details, I could go how Higgs inflation, we have non-minimal coupling, gives rise to a potential which drives inflation and produces this. So it's similar to the Star-Making. These lines are Higgs inflation. Not all of them are just simply potential. Okay? So let me go forward, please. Otherwise I finish. So the scale of inflation is going to determine whether we observe or not, with above gravitational lensing of the E mode into the B mode, this contribution. It's clear that if R is 0.2, then we're talking about a huge scale. But R could be 10 to minus 3 or so, and it could be much more scale. So we still have a quite long bigger R. What would this tell us about what we understand of the universe? Okay, physics is one of those few areas of science where we have tremendous control over a fantastic number of orders of magnitude. Very few scientists are able to have this multi-scale. Now, how does fluctuations in the CMB get converted into fluctuations in matter? No, it didn't work. Oh, what a pity. Okay, well, it was supposed to be a movie that would open up and go to one of these regions and see how time evolved from those regions, producing the first stars and the first galaxies. So here is from redshift 1100 down to redshift 1. You go from CMB fluctuations, which are 1 part in 10 to the 5, fluctuations in the matter era, rotation in matter, the glow length scale factor. Very soon those density contrasts are sufficiently large that they accrete gas onto them. The gas concentrate, they heat up, they initiate thermonuclear reactions at redshift typically between 110, and those first stars will reionize the universe. Then gas can accrete even further to form galaxies at redshift 10 and clusters and superclusters at redshift 1. Okay. So there's clear evolution from one epoch to the other. So one of the most interesting aspects of this evolution is the epoch of reionization, of which we know very little. We know from the CMB the integral of the probability, if you want the optical depth, the probability of a photon scattering from that scattering surface until us in any charge there may be. Of course, initially the universe is neutral, so there is no scattering. Eventually, reionization occurs, and a few charges are left from the ionizing energy of photons when they form stars. This ionizing energy is enough to take away the electron. The electron can act as a scattering center for the photon from the CMB. Okay? And this is going to change the energy of that photon. We're going to see the effect from the reionization in this famous tau optical depth parameter. Okay? We can measure that, but that's just an integral effect, which is simply summing up all the effects of the scattering from the scattering surface until us on the intervening gas or charges that are left. We don't know about the details, how quickly the reionization occurred, that it wasn't just a jump, a very sharp boundary from perfectly neutral to fully ionized, or was it something very, very slowly evolving? In order to tell apart, we have to use tomography. We have to understand what is the optical depth as a function of redshift. How much did the universe become ionized as a function of redshift, and whether this is in agreement with what we observe from the CMB in the third part. So if things are very abrupt, then the ionization would be seen, for instance, in very far away galaxies, which have a certain spectrum. If this was very gradual, then those galaxies would still shine at redshift 6, for instance, quasars. They would have absorption lines onto gas which is still neutral, has not yet ionized between the quasar and us. It would correspond to absorption features, they're called Lyman alpha features, in the spectra of quasars. They're called Lyman alpha because the largest production of photons from the spectrum of a quasar is the Lyman alpha line. It's mostly made of hydrogen, and this emits a tremendously sharp line, very, very luminous. Photons from those quasars are going to be absorbed by the intervening gas if it's neutral, and this absorption line will give you a feature in the spectrum. Since this occurs at different redshifts from the one of the quasar, you're going to see a series of absorption lines. By asking what is the correlation between the position in redshift. This is a quasar spectrum as a function of frequency. So this large Lyman alpha line, it's going to, in intervening gas between, create absorption features. Each one of these corresponds to a given redshift, which is related to the difference in wavelength between this and this. Okay? It's the same wavelength which at that redshift has been able to be absorbed by the neutral gas. Same would happen here. So the more absorption, that means there are more atoms, larger densities. So by looking at the correlation between positions and absorptions, you would get the density contrast. You would know how the gas distributes in space as a function of redshift. And this tells us how is gas distributed on much broader scales than you could from the positions of galaxies or the position of quasars. So we have if we have many of these quasars, we will know through auto-cross-correlation of those Lyman alpha absorption features and cross-correlation as a function of angle with some other source at some distance away from this, you could tell what is the power spectrum of matter fluctuations on those scales. So this will allow us to probe not just the epoch of ionization, but also the much later on, from redshift 6 onwards until redshift 2 or so, before the dark energy started to be relevant, before dark energy started to speed up the expansion of the universe. So in the near future, I'm talking about 10 years, thanks to surveys that I will describe in a minute, we will know these epochs with much better resolution. How does this occur? How does gravitational collapse occur? Well, we know that linear perturbation theory shows that the density of gas increases. Now the universe is expanding, so this increase of the density contrast comes together with an increase in size until gravitational attraction is strong enough that it decouples the expansion of the universe from the gravitational collapse. There's a moment, this is the spherical collapse model, where you have a maximum size of this object then collapses to form a galaxy. Of course, this will happen in different places, so the galaxies will start being receding from each other and at the same time converging to form a structure which is compact and no longer, once they decouple, no longer feel the expansion of the universe, which is the reason why we can measure it. Okay? Our rulers are not expanding. Right, so this mechanism can be done in linear perturbation theory, can be explored in certain simplified models in nonlinear gravitational collapse, but in general would require embodied simulations. So the embodied simulations start with a density contrast in the field. So your fluctuations, you set up a random Gaussian random field of fluctuations in the curvature, which corresponds to fluctuations in the density. So you set up particles in a box and you ask, once those particles start seeing the potential wells, some places you will have much larger concentrations than others, how would those particles behave? And they behave this way. The first objects which are high peaks in the density fluctuation spectrum, those high density peaks will very quickly collapse to form the first object. Quasars, very bright galaxies. Those quasi bright galaxies, they are typically on top of the crest, or above a certain threshold, and they are surrounded by objects which are also above the threshold. Okay, they typically come together in a Gaussian random field, would be together. This means that quasars would tend to cluster. You would have more and more galaxies moving, forming clusters and superclusters. What is left behind are voids, regions where somehow the Gaussian random field left less density contrast in that region. Okay? So matter will move away from those void regions and will tend to collapse onto sheets, filaments, and clusters. Okay? Fortunately, the light, let me turn off.
It's brown button.
This one?
Yeah.
No.
No,
No,
it's
it's
the
the
white
white
one.
by the door, yeah.
Yeah, thank you. So this is the structure that can be observed with this low intensity sky survey, looking at hundreds of thousands of galaxies. And you see that its structure is not uniform. It's very clear that there are voids, and there are filaments, and there are sheets, and there are superclusters where these filaments converge. So we understand our distribution around us is not uniform. Hopefully this will evolve. Maybe. Let's see whether it does. If not, I'll have to turn off. Yes, it does. Very slowly. So this is our galaxy. Our galaxy is within a group of galaxies itself, within a much larger distribution of galaxies. This has been observed by looking at tens of thousands of galaxies in our vicinity. distances of order 15,000 kilometers per second. So we're talking about 80 megaparsecs, more or less. Okay. You'll see all these points are galaxies. The fact that they look to be moving towards us is due to what's called redshift space distortion. Since the only thing you measure is the redshift, you will see the frequency of light from that galaxy, then you have to infer first what is its motion with respect to the cosmic expansion and the local motion due to the presence of more matter in their vicinity. Therefore, this is smaller, a higher concentration of mass close to it will induce an extra motion. And this extra motion you cannot distinguish from the Hubble expansion, and this will induce peculiar velocities which look like the redshift space distortion. So it's quite interesting. We live there, and it's surprising how devoid of matter we are around. All these filaments are actually tracing, they're geodesics, they're tracing the motion of galaxies at the tips of these filaments, which are moving towards a certain region, which is called the Shapley supercluster at 200 megaparsecs from us. And all these filaments are showing how those galaxies are moving. This was observed by Tully Fisher and others in Hawaii, and will give rise, I'll show you in a minute, to the famous Laniakea supercluster. There are clusters close to us, like Hercules, Perseus Piscis, Coma, Virgo, which are higher concentrations of mass, which determine, here's Virgo, here's Coma, Norma, which determine most of the motions of the galaxies that they observe. And they're determining how are they moving. But overall, there's very curious structure. Okay? This structure of filaments and sheets is what the predictions of a model of fluctuations like the one inflation produced generates. This is how matter tends to accrete if it's cold. There are no typical velocities of this dark matter, and there is no special scale on this matter. So that all scales will collapse. They will start collapsing smaller scales, they will add up to produce larger and larger objects, as indeed we seem to observe, leaving voids, leaving sheets, and leaving superclusters at the centers of those intersections of filaments. And here you have, this is Laniakea. You see, this is the basin of attraction of all galaxies that are within this volume, which seem to be moving towards the great attractor here. These red lines are other galaxies close to us, but actually moving in a different direction. So it's a different basin of attraction. So these people were able to separate the two regions which would give rise to our supercluster. They think that in 10,000 million years will become a single object, when all those galaxies will be attracted to the center. And this Perseus Piscis is the other superstructure that will end up at a given distance, again with another concentration. Notice how we are very close to a local void. I'll discuss a little bit about its consequences in a minute. Okay? I think this is fascinating that we can trace out the matter distribution around us, with distances, I said, of 100 megaparsecs from us, and tell how are those galaxies within our vicinity moving. Okay? And this motion gives your basin of attraction, and this motion distinguishes our supercluster, Laniakea, from our neighboring supercluster, Perseus Piscis. This thing, again, it's ignoring the older basin of attraction, is what we call Laniakea. All of these are galaxies which trace through their motion. You see that mostly it's a sheet, right? It's a sheet where galaxies are entering. And there are voids which surround this sheet. The same voids that we saw on much, much bigger scales with Sloan, which reached thousands of megaparsecs. Okay? But here, the local universe. Outside it, the shape. Here you see the velocities. This is how the whole picture was built up by looking at not only the position but also the velocities of galaxies. Again, we are here, not that far from the watershed that takes away all the galaxies that go into Laniakea from those that go into Perseus. It's like the ridge of a mountain, right? Water would go one way or the other. Okay. Here we are falling, we're just like surfing a wave, okay, around a very big void and going towards, from here, going towards the center of Laniakea, attracted by the mass distribution. And we are very close to the ridge. And the fact that we are close to a void might explain some peculiarities. And here I'm going to show you the mapping on much, much larger scales. Okay. This was done by the Small Sky Survey, the data release 4. Nowadays we reach data release 12. There are a factor of 10 or so more galaxies, but you're not going to see the difference. This is enough to tell the structure. The other would mean that you have many more points per point. It's not going to change the overall picture. So these are actual galaxies, real galaxies. They're put in their position. Okay, we're talking about 500,000 in data release 4. Known with exquisite precision in redshift because they would follow a spectroscopic pattern. We'll discuss about the difference between the photometric survey and a spectroscopic survey in a minute. So these are real galaxies. Okay? Excuse me. I'm sorry. Excuse me. These red ones, which we go beyond to area, they're quasars. So not only do they look at galaxies, but also quasars. They look in different directions. It's not that the universe is inhomogeneous, it's just simply that along this direction we have the galaxy, and we can measure it beyond the galaxy. So these are like wedges, narrow wedges, looking at the sky. And now we're going to go far away and see their spatial extent compared to the size of the universe, the CMB. Okay? So the CMB is the largest sphere from which we get information in light. Okay? When we detect the gravitational wave background, we will go slightly further away, but not that much further away. Okay? So this is what we observe from the CMB. Notices the tiny extent to which we know our universe. Right in the center is the Laniakea supercluster. Okay. So all these observations allow us to access through here the power spectrum of initial fluctuations driven by inflation. So if we compute the power spectrum not in the metric but in the density, there is a k component, k3 over k4, which gives you a factor k linear. This is the reason why Harrison and Zeldovich proposed that there should be fluctuations which were scaling variant on the metric, which would give rise to power spectra, which were linear in k on large scales and 1 over k squared on small scales. So how do they go? They go as follows. The CMB probes very large scales, very long waves, very small wave number of spatial frequency. The large scale structure, but they probe the smaller scales. Not quite so small, they don't reach, say, the scales that I would require to see the end of inflation or even primordial black holes, but on scales typically of order superclusters, okay? K of order 1 or so. And in between there are scales which probe both. The CMB has enough resolution with 1 that can reach Ks which are already probed by natural structure observations. So there has been already a match when I started doing research here, there was no clue about whether they correspond to each other. Now they do. Of course, this is purely statistical. What do I mean by that? What we observe in the last scattering surface, okay, corresponds to the cut that our cone, light cone, does on the last scattering surface, hypersurface. So that corresponds to a circle. Of course, photons coming along the cone will reach us. The galaxies that we observe with the logical structure are actually within this circumference, in the circle, inside the circle. They travel like their own light curves, so they move until they reach the light cone, and then its light reaches us. And therefore, we're looking at how the galaxies within that light cone, 10 minutes, yes, are actually correlated among them. But they are talking about the fluctuations which were within the circumference. They are not directly related. So if somebody tells you, oh, that CMB fluctuation is going to give rise to this, say, coma cluster, they're wrong. There is no such connection between one and the other. Okay? The CMB fluctuation has nothing to do with the fluctuation in matter. They arise from different phenomena, different fluctuations. Okay? But statistically, we can correlate the two. And among others, we can ask, the wiggles we observe in the CME, do they correspond to the wiggles we observe in the matter? And the answer is yes, indeed. Those are called baryon acoustic oscillations. So the same, remember the distance that determined the acoustic oscillations in the CME, the baryons which were counteracted by radiation pressure with respect to gravitational collapse and set up acoustic oscillations, are going to be leading a signal in the distribution of galaxies in the universe today, 13.5 billion years after. Okay, let me go forward. This scale would give rise to a correlation in the galaxies. Of course, since the universe is expanding, the scale at last scattering surface, which subtended an angle of 0.8 degrees, will have become today much bigger, actually tenths of degrees at low redshift. And we could search for this. This is a picture that shows how the density contrast, as a function of radius, evolves as a function of redshift. So here we are decreasing redshift. Initially, the peak was in the baryon. It was due to these acoustic oscillations, and eventually it was converted into a peak in the matter. So let's look at this in the mass profile rather than density profile. You multiply by r squared. It just simply makes the peak more pronounced. So here you have the gas, baryons. Photons and neutrinos decouple and move away. Gravitational collapse is going to make the dark matter itself present a peak. And this would be the correlation function. And the peak in the correlation function, R, that we would be looking for, which would have a direct connection, it's a standard ruler, with respect to the CME scale, the 0.8 degrees. So how are we going to measure this? Well, if we had a single place where you have much more problem to find a galaxy close to another one, as time progresses, this will expand and then freeze out. This freezing will set a scale, and that scale will change as a function of redshift simply because of the expansion of the universe. There's no more dynamics within it. Okay? But you could have many peaks. And of course, we're going to see the behavior of those fluctuations quite distorted because of the presence of many other peaks around. Okay? So it's extremely difficult to find the peak. It's it's of the order of 1%, 1 to 2% in the correlation function. So you have a correlation function that drops very strongly to 0 at larger distances, and within this fall at 150 nanoparsecs, which corresponds to the size of the last scattering surface projected today, or moving, you would see a little drop. That's all you need in order to tell whether those fluctuations that we see in the CMB and the distribution of matter in the larger structure correlate to each other. And indeed, this is what one observes. That, you see that this is a tiny little speck in the correlation function, this side, as a function of distance. It drops dramatically. This is 60 nanoparsecs, so if you go to 0, it will be even higher. So we've got this. And then, as it goes to 0, boom, suddenly there's a little pump. Initially, we did not have enough data to tell apart that pump. We did not see it, say, 10 years ago. In 2005, the group in Sloan, led by Eisenstein, measured for the first time baryon acoustic oscillation. Nowadays, with Bose, you can measure exquisitely that peak.
Sorry, it looks like it's increasing at large scales and at small.
This is because you're multiplying by r squared.
Oh.
Remember, then notice see the bump. You see this?
Yeah.
Okay. This is because you're multiplying by r squared. Otherwise, this would go up and this would go down. Okay. You're enhancing the errors on large scales. It is not increasing.
Okay.
There is cosmic variance at those scales, of course, but we're not going to deal with that. Okay, so in P of k, what you observe is this. So this would be the curve, and you see that. Or if you divide by this move component, so all these fall, k to minus 2, what do you get is this? So it's clear that these acoustic oscillation peaks are observed not only in the photons, but also in the barrier, in the galaxies, and in the dark matter. The first detection with Sloan was this. Now we have with CMAS, this is DR11, so with DR12 it's even better, a very clear indication of the barrier oscillation. And this allows us to, as a function of redshift, determine the distance. So here we have a standard ruler, and this is what we're going to use in order to test modified gravity. Okay? So if gravity does not behave in the way we think, like through general relativity, but it has a different component, or it has a very much more complicated nonlinear terms, it will change the rate at which the acoustic oscillation scale will evolve as a function of redshift. And we will be able to tell apart from observations whether indeed we still have general relativity or not. Moreover, since we have now data from here, that's why I insisted on the characterization of the two-point correlation function of the correlation from the matter at given redshift due to the absorption lines of the Lyman alpha quasar emission. This gives rise to a feature in the correlation function which indeed gives you a bump. And this bump tells you a scale, gives you a scale, and therefore gives you the value for the rate of expansion. So all the data points that we had until recently, except for this point, they were due to the distribution of galaxies in the near universe, say 5 billion years ago. Now, from redshift 2 or so, from the absorption lines, we can get from quasars not the period of acceleration of the universe, but the period of deceleration. Soon we will fill in all this with Euclid and with DS. We're going to fill all this curve, the rate of expansion as a function of redshift. And this is going to give you a tremendously strong constraint of modification with respect to general relativity. Okay, so not only do we have the cosmic microwave background on smaller scales, we have the intergalactic hydrogen, Lyman alpha, we have the gravitational lensing that will be used, the galaxy clustering, of course, and the clusters. So, what do you do? Well, you use surveys. What are surveys? Surveys are huge telescopes with high collecting power, which look in the sky, the largest area possible in the sky. So what they do is they use lenses in order to have a very large field of view, so that they can make photographs of the sky every night and cover a huge area. The deeper they go, the higher the redshift they can probe, and the better they can determine the distribution of mass in a larger and larger volume. Most cases, they were pencil beam, say 20 years ago. Now things have opened up and become deeper and deeper. Okay? So we're beginning to probe our environment, our local universe, up to gigaparsecs. There are two types, spectroscopic, well actually three, photometric and photospectroscopic. What's this? A spectroscopic is simply you have in your plane, I'll show you a photograph of this. You have wires, optical fibers, okay, this is your plane. You put each one of those fibers at a position of an object, which you previously have measured on your field of view, and then you take light from that object, take it through the waveguide all the way to a spectrographer, and from the spectrograph you get the spectrum of the galaxy. It takes ages. That's extremely hard. You have to make holes here and determine the position and the light from those objects. Much easier is to use photometry. That means you take a photo of the whole field, complete. You're not selecting those few galaxies which are brighter than the others. You have it, it's a complete survey. You make all the photos there. Unfortunately, since you only have one photo, you don't know you're integrating photons over all the spectrum of the object, you don't know at what redshift this is. So what do? You take many photons, as many as you can. Okay? Sloan took 5 photographs of these fields. And those 5 photographs, they were in different bands. That means rather than having a very complicated spectrum, I think I have an image, you would have 5 points on the spectrum. In some cases, it's enough to tell, so this would be the field of view, for instance, of the dark energy survey, it's enough to tell what is the spectrum of the object. So you see the difference? This is the photograph that one can do. Okay? You see how many objects you have there compared to the number of fibers that you could put into the focal plane? You see many, many more. Of course. Of all types, of all depths, of all magnitudes. As long as you have enough power and stay there long enough, then you can go to very deep space. Now, what are the main probes that these photometric and spectroscopic surveys do? First, they look for gravitational lensing. Then they look for supernova. Of course, the more supernova we have, the better we can determine through the light curves of those supernova what was the intrinsic luminosity, if you're able to calibrate them, and therefore the luminosity distance as a function of redshift. And from here, the components of the universe. Dark energy, and if it varies, the varying dark energy. You could also look for the cluster mass function. So how many galaxies you have there in a given volume. That also gives, it's a proxy for the expansion of the universe, the content of matter, and dark energy, and finally baryon acoustic oscillations. So these 4 probes have typically been searched for with different experiments. With DS, we do the 4 things at the same time. It's the same experiment, the same systematics that look at those 4 different probes simultaneously. Now, the gravitational lensing is a purely geometric effect, so out of the distortions that galaxies are seen through, they're just simply squashing of the shapes of those galaxies, changing, reducing through shear induced by the convergence field induced by matter, we will see different galaxy shapes than the original ones. We can determine the baryon content. So lensing is going to give us the matter. And how that changes as a function of time will give us the dark energy. So typically, you have huge clusters which distort images, and you can use this also to determine the matter content. Supernova. Well, you have certain types of supernova called supernova of type 1a, which very quickly dry up and slowly decay. You can also have the spectrum, and from here you can determine the luminosity distance or modulus function as a function of redshift. The best results nowadays tell you that the equation of state of dark energy, whatever that is very close to -1, to within a few percent, 5%. And you can see it here. It has reached redshift 1.4 in the last published catalogs. With DS, we already have reached redshift 2, and we have something like 2,000 supernova. It's not yet published, it will become soon. So we go from 700 or so supernova to 2,000, and much deeper. Okay? So DS is going to revolutionize in supernovas, the field. All these discussions that Julius Sarkar are putting on the web, we ignore.
Sorry, Juan.
Yes.
You deal with theories beyond GR, right? It's always that claim that it would be better to measure the total quantum state rather than isolating the dark energy one.
That's true. That will be able to.
Would it be a problem or
no?
Yes.
No, fortunately with DS, the only difficulty with DS is their photosync. Okay, because we only have a photometric survey, and therefore we have uncertainty in the position of galaxies, which could be 1% or so, 1 to 2%. The best we can do here. That means that you don't know where those galaxies are within a few percent. Now, if you can do bins in redshift, since we can go all the way to redshift 2, 1.5 to 2, okay, then we can ask, how does this equation of state vary as a function of redshift? So we're going to know the evolution of the equation of state with redshift. Because the same analysis that you do for a given slice, you do for the next slice and for the other. So we're going to measure not just W0, W8, and most probable through the growth of structure, we will measure not just the background evolution, the expansion of the universe, but also the growth of structure, the rate at which structure grows, through redshift plate distortion and through Baryogenesis oscillations.
Taking into account the scale for the growth factor.
Taking into account both the scale
And
and K and Z. Unfortunately, as I said, the redshift determination of objects in DS is not so good. We have photoseta, photometric redshifts, and we would be much better off if we reduce increase the sensitivity and would be able to go down to photosets of few per minute. For this, we will require a different type of service, this photospectroscopic service that I was advertising a while ago, the ones I'm involved with. It's POW, Physics of Accelerating Universe service. Okay, so not only do we have lensing and supernova, we also have galaxy clusters. They are dominated by dark matter. It gives you mostly the gravitational attraction. We know the number density, and that's very sensitive to the cosmological constant expansion, because as expansion sets those apart, the number of those that you measure is very closely related to this dark energy content. So dark matter attracts them, dark energy separates them, and you can deduce what is the different components. You can segregate dark matter from dark energy. Also, I didn't mention here, not just the correlation function of clusters, but also of voids. Because in voids, you've lost galaxies. Galaxies have gone to the sheets and to the filaments. They're no longer there. So most of the voids is full of dark energy, not dark matter. So that's a natural way to segregate dark matter from dark energy. So if you look at the correlation function of clusters, and you look at the correlation function of voids, and the shapes of voids, and the rate at which those voids increase, you will have some insight into the amount of the character of dark energy, rather than that of dark matter. It's something which I am leading in the dark energy survey and in those efforts. Okay, so what are those experiments? This is me in front of the Blanco telescope, the day we inaugurated the survey. It's in Cerro Tololo, in Chile. It's called the Blanco telescope. It will measure 500 million galaxies to 5,000 square degrees in the sky. That's an eighth, an octant of the full sky. It's of course in a region where we don't have the galaxy, the Vega galaxy, we're looking to the south. It has 5 or even better, maybe 3% possibly photosea error, 1%, and we can do 20 bits. And here's where you're asking. By having more bits, you will be able to tell what is the velocity evolution. It costs $100 million. So this was the inauguration on the 8th of November. For you to make an idea, these are wide field surveys. So this is the field of view, and this is that of the moon. Imagine it's like 8 times or so. It's very broad. So we can do a photograph here, then shift, another photograph, shift, another photograph, and so on. Fill up the whole sky with planes. So the high resolution spectra will be looked at in only 4 or 5 bands. So you're going to get 4 or 5 points out of a very complicated spectrum. Most cases when you have galaxies that have a very flat spectrum then suddenly jump up, corresponding to some physics related to the way those stars are formed, then these break at 4,000 angstroms will very clearly be seen if they are redshift 0 by the 4 bands, will not be seen by the first band, but it will begin to be seen by the other bands and so on. So there is a way using photometry to tell where the object is. Of course, since the bands are wide, you have an uncertainty, and that's what gives you the uncertainty in the redshift. Okay? As simple as that. If you had many more bands, as we will have with power, the better you will know the redshift. It's good, like Ullmann's spectroscopy. So this is the footprint. It has been searched, now we have the full footprint. This has been observed in their 3-year footprint, already covers the full box. It's not the full depth, but it is the full footprint. These are the supernova fields, looking in different directions. This was science verification areas, and this is year 1. So this was year 2. In Spain we have 4 groups, CEMAT, in Barcelona there's the IFAI, Instituto de Física de las Energías, and IEC, and in Madrid, it's like 300 people from 20 or so institutions. We know each other, all of us know each other. Sufficiently small that we can follow. So In W0WA, I didn't go into this. Perhaps Oscar will mention. No? No chance? Okay. So this would be the value today of the dark energy equation state, and this is the variation of that equation, that state with respect to its scale factor. So dark energy as a cross-functional constant would be W0A and W0 minus 1 and WA 0 at this point, fiducial point. And the sensitivity of DS to weak lensing, variable oscillation clusters, supernova, etc., will give you this kind of constraints. Nowadays, the area is like this, so we're going to reduce by a factor 10 or so. Data is not yet out. What about improving our photometry? If we can go down to few per mil rather than few percent, even if you don't have that many galaxies or you don't have such a large area, you can do tomography. You can try to answer Albert's question with much higher precision. So now your bits, rather than being, say, 0.02 or 0.05, they're 3 per mil in width. So you know exactly where those galaxies are. So you can do very fine tomography. Ask how does the equation of state change as a function of redshift with high accuracy. So these are the 5 bands from DS, and these are the bands from Tau. Many 100 angstrom width, and it's already taking data. This is the resolution that you will be getting W0WA. The resolution with respect to the DS. It's already in place in the William Herschel telescope in the Canary Islands. This is our camera, we built it. I didn't build it, I didn't screw any of those things. I just helped designing, and it was built in CMAT and E5. People that had expertise from particle physics that moved into cosmology. And we placed this in the focal plane, in the primary of the William Herschel telescope in the Canary Islands. This was the first image. The Whirlpool Cat and 51. It's a beautiful image. So PAUS, compared to other surveys which are in the game, occupies a very interesting position. So it has a relatively small area compared to Euclid or balls or DES, but it has very large number of galaxies per square degree, density of spectrum, and has a very high resolution in redshift. Area and number of spectrum. So it's very well located within the other surveys. So in principle, we should be able to get extremely good results, and I hope within the next few years results will come up. Of course, the ultimate thing will be having a full sky survey called Euclid. Yes?
A small question. So when does peculiar velocity come into play? Because at some, like you can't really distinguish.
Peculiar velocities are going to impose redshift space distortions on the position of galaxies. Okay? They will be small at very high redshift when the gravitational attraction of the intervening mass will move those galaxies beyond the Hubble expansion and will induce the peculiar velocity. So at high redshift, because the density contrast is still small, you don't expect those effects to be large. At small redshift, 0.2 or so, they will be dominant. Clearly, galaxies will fall into the potential wells and they will move with respect to the expansion, and you'll see a deviation. So how quickly that moves as a function of redshift, you see the difference from high to low redshift, is going to tell you about the growth of structure and the effect of gravity on the formation of structure. Okay? So if at large redshifts we observe peculiar velocities or redshift space distortions, which is how you get to those peculiar velocities, which are in agreement with cold dark matter paradigm, and as a function of redshift, as we go closer and closer, these peculiar velocities are larger than you would expect from ordinary gravitational collapse, then you have some instance that you can deduce that other type of gravity is acting.
So you can take that.
We will be able to measure. But for that you need very high redshift resolution.
Okay. Because I thought instead that, I mean, they put like lower bounds of the resolution in redshift, because at some point you can't really tell if it's cosmological or if
only at small scales, at low redshift.
How low? 0.2?
0.2.
0.2.
0.2.
Okay.
0.2. So it's a nuisance for determining the expansion of the universe, but it's great for determining the growth of structure. Okay? Now, as long as they're small in the high redshift universe, redshift 1 or so, where still dark energy has not played any role, it's only dark matter out there producing those peculiar velocities, then you can trace what is the behavior of gravity there and move as a function of redshift to lower redshifts and start to see the deviations if there are any with respect to geometry. Unfortunately, Euclid, what I'm going to describe here, does not reach sufficiently low redshifts. What I wrote here was wishful thinking. We thought that the objects that Euclid might be able to see, we might reach 0.5. That's not true. We're going to, at most, 0.7. From 0.7 to about redshift 2 is the range of redshifts that Euclid will be able to measure. We cannot go below 0.7, unfortunately. Which means that all these features of growth of structure due to modifications of gravity, modification of dark energy, are not going to be probed by Euclid. It's going to probe very good the initial conditions, but it's not going to probe the evolution through gravitational collapse. For that, we will need something like power.
Why is it wishful thinking?
Yes.
Why is it wishful thinking that you want to see things closer?
Good. Because the objects that you use to determine the distribution of mass are very peculiar. They are light-emitting galaxies, extremely luminous, ELGs. They are not ordinary galaxies. Okay, the ordinary galaxies you will not be able. They don't have sufficient sensitivity because the telescope that you put up in Euclid has to be reduced because of weight. You cannot put a huge telescope, a 4-meter telescope like we do with DS or with the William Herschel telescope. It's less than 2 meters, 1.5. Therefore, the collecting capacity of light to tell objects apart is reduced. You have to use special objects. They're called line-emitting galaxies, okay, ELGs. And these galaxies, they have been understood nowadays that they do not populate with sufficient numbers, density, at low redshifts. So you're not only going to see them beyond 0.7. So that was not known when the whole Euclid survey was thought of. And now we know. Unfortunately, we have to be less ambitious.
Do you think these evolve into something we'll do this time?
Yes, that's right. They do. Yeah. Indeed. There's a peak in stellar formation, which is at around redshift 1. And then it starts decreasing. There's no longer any star formation which will be bright enough to be seen by a telescope like the one in Euclid. And that's it. You lost it. Okay? It's quite unfortunate because, as you can see here, it's $1 billion and not just 100 million. Okay? It's true that it's spectroscopically, you can go to 1 per mil, which is better than 3.5 per mil. Okay, but this is only for 100 million galaxies. Well, it's not bad. It's only 100 million, but it's for redshift 7 only. Now, it not only has a spectroscopic survey, it also has an imaging survey. So it's making images also. And these images will go all the way to 1,000 million galaxies. They will cover 15,000 square degrees, but with a very bad photometry. It doesn't have enough filters to resolve those objects. Even though it has many more, its uncertainty in photo C prevent them from doing tomography. Tomography cannot be done. Okay, and with this I end this part. Maybe I've gone over time, I'm sorry.
That's fine.
A few minutes. So let me recapitulate before tomorrow's lecture how quantum fluctuations during inflation, which set up those curvature fluctuations which were traveled still without matter inside, okay, until they went through reheating of the universe at the end of inflation. At reheating, those curvature fluctuations, they were, if you want, like the ripples that you see in the sand when the tide has gone away. It has left ripples in. So the tide is inflation, it has left those irregularities. When the tide goes away, you still left the irregularities in the space-time. That space-time will be filled up with the energy and the matter that has come from the decay of the inflaton. So there will be like weeds and seeds at the bottom of those potential wells. That is the dark matter and the photons and the radiation, which permeates space-time and falls into those potential wells set up by inflation. Eventually that matter collapses to form structure. We're going to see them both at the CME and in the logical structure distribution. So we will have a way to determine from how matter is behaving what was the initial fluctuation, what were those ripples when the tide went away. Okay? By knowing the cross-correlation on larger scales, we will be able to connect the CMB and the larger structure, but we still lack sufficient resolution on small scales where things become nonlinear and it's much more difficult to extract the primordial spectrum from, that will tell us about what other physics occur during inflation at much smaller scales. And tomorrow, I'll use this to open a new window into the early universe by searching for the character or the nature of dark matter. So not only do we have CMB anisotropies, both temperature and polarization, through photons, we could also eventually detect the gravitational waves. There are two ways to detect those gravitational waves. You could look at the gravitational wave effect, just like the ripples in the sand when the tide leaves. It produces ripples from which photons will scatter off. And these ripples, which are tensorial character, they produce shear. These ripples act very strongly, not just in the temperature, but also in the polarization. And this will be seen through indirect effects of how the gravitational waves from that epoch has left their imprint in the polarization of photons. But we may continue those gravitational waves, of course, they're simply redshift, they don't interact at all. It's true they left their curvature on the last scattering surface over which photons left, but they still continue evolving until today. So if we have detectors sensitive enough, and we know that we can measure the inspiraling of two very massive black holes. So for the first time, we have detectors that are able to see gravitational waves. Of course, the gravitational waves that these detectors are going to measure from inflation are not these high pitch objects, this chirp behavior in the frequency. No, it's just going to be cacophony. It's going to move those detectors around as in a stochastic background, as if it were moving with some temperature fluctuation. But it's not temperature, and this can be separated from the temperature by doing integration. Okay? So the gravitational wave background eventually might be measured by LISA, possibly in space. Those on the ground might not be sensitive enough. And then we will have an indirect determination of the amplitude of inflation from detection today and from the CMB. Just as much as we know that something like Big Bang equals must have occurred to give the baryon abundance that we check when the universe was 1 electron volt at the CMB and when it wasn't a mega electron volt in the early universe 1 second after the Big Bang. Those cross correlations of phenomena in the universe will be the regular thing in cosmology from now on. We are going to measure things in many different ways. We're going to have a multi-probe, multi-epoch approach to cosmology that we definitely did not have 20 years ago. Okay? So the future is bright, and I'm sure we will try to understand from our standpoint, 13.8 million years after the Big Bang, what happened at the Big Bang during inflation. Okay, so tomorrow I will continue then with what happened at preheating and what possibly happened at inflation. Any questions?
Yeah.
Yes?
So with all these surveys that you just showed us, where they constrain W0 and WN, do they leave omega k as a free parameter, or set it to 0 for these constraints?
Right, this is something which we are at present trying to determine whether we have enough resolution within DS to be able to tell the scale dependence. In principle, scale dependence is an issue. The difficulty is that it gets very strongly tied with gravitational collapse, because it's clear that nonlinear gravitational collapse is not to occur equally on all scales. Okay? So then the difficulty has to do with not just what are the correlation functions on angles, which we can measure very precisely, because we have photometry, we know exactly where the object is, so we can ask how probable it is that these two objects are correlated. Okay? Our difficulty is as a function of redshift. Okay? So we're going to look for the dependence on scale as a function of depth and not of angle. And this thing is going to hamper your ability to determine things like the scale dependence.
Okay, I actually meant the curvature, okay.
Oh, the curvature.
Yeah, so usually when you see those constraint contours,
it's going to be very difficult to see the curvature
like
with a survey that has 5,000 square degrees.
I just mean the constraints on omega naught and omega A are degenerate with curvature, right?
Yes.
So just in the analyses, is it standard to set the curvature to 0?
Yeah.
Yeah.
It is. So we are assuming that the curvature we observe in the CME has evolved not much faster than you would expect from standard lambda colored matter to the redshift at which we observe those galaxies, at which we want to measure WC and WA. So we don't expect curvature to play a major role. As I said before, the difficulty with this is not just the measurement but the systematics. And the systematics are very different in the 4 different probes: supernovae, clusters, galaxy clustering, and baryogenesis oscillations. So they are good, and weak lensing. Those different systematics will be used in order to try to disentangle from there the common physics to all of those. That's how the different diagrams seem to be used to break degeneracies. But there will always be degeneracies on our systematics, our theoretical systematics. Okay? If the results, like with Planck, are sufficiently precise, then we can go beyond those systematics, observational systematics, and start to explore the theoretical systematics, then we will do it, obviously. Everybody wants to know whether there is a sensitivity to curvature, whether there is a sensitivity to scale, that I was answering before. There are many different aspects, for instance, non-Gaussianities, etc. There are many things that come hierarchically in our approach to the data. So the first thing we would do, test lambda colored matter. The next thing we would do, go for W as a function of scale. The next thing we might go is look for curvature, etc., etc., etc. Okay? As usual, with the amount of data that we have, we can do as best we can. Okay? It might be that the photo C probably is the worst systematic. The fact that we don't know the positions of galaxies within DS to a precision better than a few percent is going to hamper our ability to tell about curvature, to tell about scale. It will require a future survey, which is now being planned, it's not approved yet, which will do both photometry, but as we do with 40 bands rather than 5 bands, as we do with the physics of accelerated universe survey. Okay. There is a survey to which I'm a member of, which is called DESI. It's going to do it's like big BOSS. No, it's going to go much beyond BOSS. It's going to measure 100 million galaxies with spectroscopy, very high spectroscopy, rather than having holes in the plane, focal plane. Remember that there were holes in the Sloan. Okay, you had to know exactly where the object was before you drilled a hole, put a fiber to go to a spectrograph. Here you would have robots that would follow the positions of galaxies. So you have your plane totally filled up with little robots, 5,000 of those, each one of them searching for the light of a given object. And they are moving, so you could do this robotically, automatically, rather than having to drill holes, you just simply using the direction of those robots to tell the light coming from that object will go through the cable down to the spectrograph. And every 300 seconds, you change your slide, you've made your observation, and then you say, now go to a different direction, and they move the robots. And they look in different directions, and so on. They do that like 10 times per night. And with this, you can cover, in DESI, we will cover something like, what was it, 8,000 or 9,000, that's still a result, square degrees of the northern span. It's at Key Peak, and it's a telescope very similar to that of the Planck telescope. It's a 4-meter telescope with a huge field of view. This is underway. Then we will have the large synoptic telescope, the LSST, in Cerro Pachón, in Chile, which will do both photometry and spectroscopy. So the future is really bright in logical structure surveys. But it will come to an end. With Euclid, it will just simply, you will know all that you can in galaxies to a given redshift. So the next step is to go beyond galaxies. Go search for gas, hydrogen. Go for the 21 centimeter line that South Africa in particular is doing a tremendous effort through this square kilometer array. Okay. And that's the future, clearly. In fact, that's why I was attracted to come here and give some lectures, because I think it's absolutely essential that we make the jump into that realm. Because we will not be looking at things that can be probed all the way to redshift 2. No, we will go all the way to redshift 20. So that's a tremendous amount of volume. We're going to probe the evolution of the power spectrum from redshift 20 to redshift 6 to redshift 2 possibly, with very high accuracy. And that is going to set up the initial conditions for what we observe on large scale. This will be crucial for understanding the evolution of gravity since then. When the universe started to be sufficiently big, the things deviating from what we observe in the solar system might be relevant. More questions? Okay, well, I'm still here. We can continue tomorrow.
Thanks.
Thank you.